So I propose we slowly start with the introduction. I think that more people are going to join, but they are going to join during the beginning of the webinar. So we are very happy to have you with us today. Thanks for taking the time to participate to our webinar on the barriers that may exist in the HPC world and the numerical simulation world. We are thrilled to be joined by Maxime Guéguin of Symvia and François Mazen of Kitware to accompany us to this for this webinar today. So maybe a few words on the logistic. So if you have any trouble hearing us or trouble with the sound or any other trouble, you may use the 9 dots that you have on the bottom right of the meeting, and the question section will let you ask question and let us know if you have any trouble hearing us or seeing the slides that we are sharing. So it's on the bottom right, the 9 dots, and then you have a question section on which you can write us. So as I was saying, we are thrilled to be joined by Symvia, a subsidiary of EDF, Electricity de France, and Kitware, the company behind ParaView, for today's webinar, where we are going to share how our view align on the democratization of numerical simulation and HPC. So maybe before starting with the how to break down the barriers, we can start with the why. Why is numerical simulation a must-have for innovation? Here we have a sketch. On the left, we have the traditional way of putting out products. As you can see, we have a design phase that then leads to a physical prototype phase on which we are going to perform tests. With this way of doing things, the issue is that, for example, let's take a plane. When you want to build a plane, you have to build physical prototypes of planes, or at least subpart of a plane, and then bring them to some tests, so wind tunnels and things like that. And then you have to assess whether or not the prototype that you've built is up for the production, so for mass production or not. So this way of doing things is very costly, because you will have to build a lot of prototypes before having your end products. And this is where numerical simulation ultimately helps, because although it adds steps in the building phase, the steps allows for more design optimization and validation and faster iteration. So ultimately, some of the tests that will be performed in the physical world with things like wind tunnel in the traditional way of building products will then be moved onto the numerical space, which allows for more iteration. So in the end, we have a better product, more time in the design iteration, the design exploration phase, and this leads to faster iteration. And we can also hope to build more product with less resources than we would with the traditional way of doing things. But even though this allows for building building products faster, there are some blockers that remains to truly be able to use the numerical simulation to one's advantage. And the first one is the infrastructure management, because to be able to perform numerical simulation, you would have to manage all of the layers that it takes to perform those simulations, which also means a lot of upfront costs, because to operate your own resources, you have to be on the CapEx side of expenditure. And then once you come all this way, you have to be able to make the resources available for your engineers team, which can be a challenge, even especially when you've built your resources for a few number of years. Then you have to be able to share the resources with all of the team for this number of years. And then those barriers brings consequences. There are missed opportunities for the innovation. The real mean of innovation becomes the resources that each companies would have, and this is something that we want to break down, because the opportunity to bring innovation with new products should not be limited by the resources, and so the missed opportunities, the reduced ambition, and the competitive net gap should be overcome by having access to HPC and numerical simulation, no matter the resources that you have. And this is what Qarnot aims to do, to lift the existing barriers. Our mission and our objective is to bring the infrastructure, the HPC infrastructure that is required to perform numerical simulation, to make it as accessible as possible for all CAE engineers. So our mission and our vision is to take on the IT, where you can focus on your expertise, which is the actual physical analysis of your cases. So this is where Qarnot comes to play, and I will now let the floor to Maxime to explain how Symvia takes its part of this democratization objective.
Yes, thank you, Théo. It's a pleasure for Symvia, for me, to share this webinar with Qarnot and Kitwa. First, I will talk about EDF because, as you said, Symvia is a subsidiary of EDF. So the simulation in the EDF world is based on in-house software, which are developed to support the business of electricity production mainly. So as you can imagine, if you want to design a nuclear plant or a dam, you will have multi-physics software in order to do the designs that you need for this kind of system. So the choice of EDF was to develop its own software, and it was over 35 years now. So it's quite a long time of development. And maybe 25 years ago, EDF decided to put these codes as open source. So it was quite of a pioneer for this kind of dissemination. And it was really important for EDF, especially in order to be transparent with the safety authority related to nuclear facilities. So nowadays, we know that around 500 engineers are using this software every day at EDF, but because it's open source, we also know that these codes are used by, let's say, around 10,000 users all around the world. So it's quite impressive. But a few months ago, EDF decided to launch Symvia. So as you will see on the next slide, the idea of Symvia is to help more and more users to use this kind of software. So for the moment, what we have at Symvia on our portfolio, there are 4 software. The first one is Salome. It's a platform where you can do the geometry, the mesh. You can bring your own solver if you want to, and you can also visualize the results. It's based on ParaView, and François will give you a little bit of a demonstration of what you can do with ParaView, which is quite impressive. The other software that we have dedicated to structural and analysis and solid mechanics is called Qarnot. The third one is OpenTelemac, and it solves the Saint-Venant equation for environmental hydraulics. And last but not least, Qarnot. I will talk about this in a minute, but it's a CFD software. So what do we do at Symvia? We have a paid offer to help more and more users to use these codes. So it's based on training, technical support. We have PhD engineer at Symvia that can help for physics and for software development. Also, if you want to bring together Qarnot and Qarnot in your own environment, we can help to develop some plugins and to have some specific features if you need to. And we also work with some partners to have cloud access, especially with Qarnot. So that's the paid offers that we have. And we also have a strong commitment for the community of users. So we try to have this kind of free webinar. We have some tutorials on our YouTube channel and so on. So that's the idea, to have more and more users of this code. But let's talk about Qarnot. So as I said, it's a CFD solver. You can see on the right that there is a graphical interface where you can, based on the mesh that you have made with Salome, you can define the boundary conditions that you want. You can use some turbulence models, RANs or LES. You also have access to specific modules because it's developed by EDF. You have some application-related combustion, atmospheric simulation, particle transport, electric arc, and so on. So it's quite a huge variety of models that you will have, and you also have some multi-phase features, free surface flow and volume of fluids. So, but because it's developed by EDF, you don't need to think that it's only applicable to EDF application. You can also run some airflow dynamics, some turbo machinery, manufacturing processes. You have several types of real-world applications that we see every day in the literature. And the third part of this slide is dedicated to HPC because the idea of the software is really to be HPC compliant. It runs on massive models, usually at EDF. So the idea was to have a strong separation between the graphical interface and the massively parallel solvers. So that's done with Code Saturn, and also a focus on parallel in situ pre and post processing, which is quite important. And I think François will agree on this part. We also have a great work on the scalability, and the next slide will be dedicated to this, but that's a showcase on what can be done with Code Saturn. So here's the idea for the webinar was to have an illustrative use case. So it's a simplified geometry of a blade in a rotor engine. So we took the geometry from GrabCAD, which is an open source library with geometry. We clean this with Salome. We have done the meshing also, and we run a K omega SST turbulence model in order to have the behavior of this system. And we want to have the temperature and the pressure at the surface of the blade. So it's a simplified version of what can be done in the industry, but it's quite interesting. So here we have the air that enters at 100 meters per second and 400 Kelvin, and we need to have access to the results at the surface of the blade. The idea for this kind of use case is to then combine the CFD solver, CFD analysis, with a thermal analysis of the solid that can be done with Cadaster in order to have the distribution of the temperature inside the blade. And then you can run your nonlinear thermomechanical analysis if you want to estimate what will be the long-term structural integrity of your system. So for the matter of the benchmark, we launched this on a little bit more than 2 million cis-radial elements and 2,000 iterations. And you will have access in the future to this model if you want to run it by yourself. So for this benchmark, we worked with Qarnot. We ran it on Intel Xeon processor. The idea was to enable MPI parallelization, and we test this with a sequential execution and up to 28 cores execution. So as you can see on the right, you have the total runtime scaling, and also, if you want, it's more. It illustrates also the speedups that you will see. So you can see that up to 10 cores, you have near perfect scalability. That's something that is interesting. And also, if you compare the sequential execution with the 28 cores execution, you will have a computation time that will be reduced by a factor of 20. So it's something that can be interesting. And of course, with Qarnot, you will have more and more cores, so you can do the scale up by yourself. The last thing that I wanted to say is the fact that something is really interesting when you use the HPC world is to have the entire process in the same environment. And that's something that you can do with Qarnot because you can script every task that you need to do. You can keep your intermediate results in the Qarnot environment. And if you want to run a Code Saturn simulation and after this Cadaster simulation, you can stay in the same environment. And it's quite interesting when you want to do a full simulation of this kind of complex system. But now Théo will showcase how to run Code Saturn on Qarnot.
Exactly. Thank you, Maxime. So what I suggest is that we move on to the actual platform to show how we can launch this very case on Qarnot's infrastructure. So here on my screen, now we have the platform, the access to the platform that allows us to launch simulations directly onto Qarnot's infrastructures and hardware. So how to launch the motor blade case that Maxime just detailed? We can go on start a simulation, and the idea here is to have an interface that is as simple as possible for every engineer CIA user. So the idea is that you don't have to put a lot of effort to understand how the case will be launched on your clusters, what will be the interconnect between the nodes and things like that must remain on the IT part. What we want is that from the first time you log in and then the time that you have a simulation running, we want this time to be as short as possible. And so this is something that I will try to show you. First, we can choose the name of the simulation. So here we will have a motor blade case run on Code Saturn. And then what we can do is just choose from the catalog Code Saturn to tell to choose the environment, the software environment that will be solving our case. We choose the latest version of Code Saturn, which is already integrated onto Qarnot's environment. And then we can go to the next step. So far we've chosen the software environment. Now we are going to pick the actual files that we want to bring as inputs to our simulation. So as you can see here, I have access to several directories that I can also find here with the Explorer. And those directories contain all of the files that I need to run some simulation. So here I will just go for the Code Saturn directory that I've already uploaded, and that contains the actual working directory with all of the inputs, so the motor blade case that we've just talked about. So now what I will do is launch a batch simulation. So I can specify the actual working directory that is within the directory that I've just chosen. So the Code Saturn directory, if I show you its content, here I have the actual case that is the motor blade case that I can run. So this is the name that I will pass on to the servers so that they know what is the working directory, and then be able to launch the simulation. So far we've chosen the software environment, we've chosen how to deal with the data, so what are the data that we are going to bring to our simulation. And now the last step, the last mandatory step, is to choose the hardware and the way we want to consume Qarnot's infrastructure. So as you can see here, we have the pricing plan, which consists of 3 options. The first 2 are options that will consume the credits that I have associated with my accounts. For large enterprise, we can share the credits with between several accounts. The difference between the 2 is the priority. So on the first option, on the flex option, if Qarnot encounters peak loads demand, then the computation that you launch may be preemptible, which is not the case with the on-demand pricing plan. This also translates to a more economical approach for the flex pricing plan compared to the on-demand one. The last option is the reserved option. So this is the same thing as renting a server, one of Qarnot's server or several servers for a given period of time. If you know that you will encounter needs for the next 6 months, you can choose to have a server that is dedicated to you for the next 6 months. And then you will be able to just launch simulation on those servers without having your credits depleted by the simulation time that you spend with your cases. So here for the actual example, we are going to choose the on-demand pricing plan. And then to follow the example that Maxime just talked about, I'm going to choose the 28 cores, so the dual Intel Xeon servers to run the case. So far, we've chosen the software environment, the way to deal with the data for our simulation, and now we've chosen the support, the hardware support that is going to welcome all of this case. From our point of view, here at Qarnot, we have everything we need to launch the simulation. As you can see, I can already start the simulation. But if you want to gain a finer control on your simulation, you can go to a 4th option that is optional, a 4th step, those are the advanced settings. So here you will find some parameters that help you have a finer control on your simulation, such as the snapshots, for example, which consist of periodical backups of the contents that are generated by your cluster during the run. So that if you have a very long run, we know that this may be the case for CFD application, you will have regular backups of the content of your cluster. You can also choose, for example, to directly add a post-processing script so that the raw result that you get are not the results that you exploit, but straight after the simulation, you upload, for example, a Python script that will conduct some manipulation on the raw data so that you only retrieve what really has added value for your analysis after the simulation has run. And then for the post-processing, François will talk more about the option that you can find on Qarnot. So this is it. We have everything we need to launch the simulation. I can now start my case, and I will go back to the main dashboard where I can see that my case is being submitted. As you can see, I've already run it, and when I open it, I can see the details that I have on the task, because we know that, as I said, the simulation may be long ones. You need to have feedback from the cluster to know what is going on, if the simulation is converging, diverging. Do I need to let the simulation run for a few more iterations, or can I stop it now to start my post-processing actions? Those are all things that you need to know during your run, and those are things that the interface allow you to do. So as you can see here, I have all of the logs that are generated by CodeSaturn. I can follow how well my simulation is going. If there are errors or warnings, I will find them on this particular tab where I have all of the infos that the CodeSaturn is generated. And then if I want a more graphical approach to the follow-up of the simulation, I can choose to go to the convergence plot, where I will be able to monitor the numerical residual of the simulation, and I can choose to adapt the time range that I follow to be convinced that my simulation has actually converged to a given value. So as you can see here, if I go to the last step, we can see that the residual for the velocity, for example, has dropped below some values, and we can consider whether or not the simulation has converged. So this is everything we put in place to allow you to have feedback from the simulation during the simulation. But as we know, for CFD engineers, the analysis is also a big part of the run that you will have to make. You will have to gain the physical sense of the case that you've run. And this is where ParaView and Kitware comes into place to allow you to analyze the results that you've gained from a done simulation. And so this is where I will give the floor to François, so that you may, I'm going back to the slides, so that you may.
Yes, thank you.
Talk more about ParaView.
Perfect. Thank you, Maxime and Théo, for this nice presentation. I'm very happy, as Maxime said, to participate in this webinar. So I will introduce shortly Kitware and ParaView to you if you're not familiar with the company and the product. So Kitware is a medium-sized company, about 200 people worldwide, with offices in the US and in France, where I'm from and where I'm located at the moment. Our focus is to develop open source software for science and for open science in general, with a strong commitment in data analysis and data visualization. And we are really a tech-oriented company, as most of the people in the company are people with some strong graduate degrees. For instance, I'm a mechanical engineer and software developers, even if nowadays I'm the director of the ParaView team in Europe. So in the next slide, we will see some of the product we develop or we co-develop. Actually, we have more than 40 products that we support at Kitware. And usually we call them more than product. We call them usually platforms, because as they are open source, you have access to the source code. You can modify it, change it, redistribute them, and also even sell them in another product. And for instance, the Salome software from EDF that Sylvia just presented, that Maxime just presented, the post-processing part is ParaView integrated into Salome and rebranded as ParaViz, for instance. So this is a perfect example here. So about the name, as you can see, today we will talk about ParaView. Yeah, the slide before, please. Perfect. Maybe you also know VTK, which is the library behind ParaView, but we have lots of other products linked to, for example, medical imaging like ITK or 3D Slicer, TomVis for tomography, LiDAR-View for LiDAR and sensor visualization, Monai for AI in medical imaging, and so on. And our biggest product, for instance, is CMake, the one on the top left, which is a tool to configure C++ build, widely used worldwide. And Kitware as a company, we develop free software as they are open source, and similar to Symvia, our business model is to provide services. So this is the box on the bottom of this slide. We can provide trainings, how to use ParaView, how to use VTK, how to use CMake. We can support you during your usage of this product. And of course, we can do some custom development, and we also participate a lot in collaboration with university academics, with some national grant or European grant, for instance, from France here. So we can move to the next slide, where I would like to introduce now ParaView, which is one of our flagship products in scientific visualization. So this is a tool, 20 years old, 25 years old or something like that, open source, of course, widely used in industry and research in order to analyze large data and also to visualize the output of the analysis, with a strong focus on massive data set. So ParaView is now part of the standard software stack on every supercomputer in the world, like the top 500 we have here. And with ParaView, you can extract meaningful information from your data. Your data could come from numerical simulation like Code Saturn, but also from experiment or from mathematical equation also, so any kind of data actually. And ParaView is a quite generic tool. Here there is some example like fluid dynamics, structure analysis, medical imaging, particle simulation, astrophysics, geoscience. This is some domain-specific application we can where you can post-process your data with ParaView. And on the next slide, I will close the ParaView presentation. So ParaView has a client-server architecture. This is what that led ParaView to open very large dataset, a massive dataset on a cluster, and to have some remote rendering. And thanks to this architecture, we have a big ecosystem around ParaView. We have the desktop client that I will just showcase in a minute. But we have also lots of bridges like the web visualization. We can connect some browser to also visualize data. We have lots of connection with the Python ecosystem, which means that you can do anything in batch mode, similar to what you can do with the Qarnot infrastructure and Symvia. With Python comes a big ecosystem. You can do also machine learning with PyTorch, TensorFlow, also NNX for surrogate modeling, for instance. And we have also some more advanced visualization like virtual reality, advanced reality with OpenXR, Jupyter Notebook, and also in situ analysis with ParaView Catalyst. So we have a big ecosystem around ParaView as soon as your data could live in the ParaView server. Okay, so I will move to the demo time. I think I will share my screen right now. Okay, can you see it? Yeah, perfect. So I just opened a graphical session on the Qarnot infrastructure. So this is VNC with the web client. So it runs in my browser, in the Chrome browser. So I just created the standard visualization session, and we can see we have some nice hardware available, 64 cores, 126 gigabytes of memory, and we have two NVIDIA RTX graphic card A6000 with 49 gigabytes of graphic memory available. So this is quite a interesting hardware to use for post-processing. So here, this is ParaView provided by Qarnot. And so I open in the software the simulation results from Code Saturn that Maxime just showcased, and which has we did run on the Qarnot infrastructures. So if you don't know ParaView, so quick training, everything will happen in the pipeline browser. This is the first thing to understand. In the pipeline browser, this is where you open your data and when you modify your data in order to extract things and to visualize. So here I just opened the 2 CGNS file from the Code Saturn simulation. And to display something in the 3D screen, which is in the middle here, we just click on the eye close to the name of the file we just opened. And here we have a first data which is displayed, which is a big box output of the simulation, the boundary. And the second things to know when you use ParaView, besides the pipeline browser, is that you have two other interesting combo box here. First one is to manage how you want to represent your data. So this is a representation. By default, this is a surface, but we can move to wireframe, for instance, to better visualize the mesh. We can also superpose the mesh with the surface. We can also move to point representation, point Gaussian, for instance, and so on. So this is the first things to know about ParaView. The second one is usually with some data, you have some fields on the data, so some pressure, temperature, stress, and so on. So you can use the second combo box here to choose the one you want to display. Here we have, for instance, some stress data on the mesh. So let's display it. And now it's color based on some color map. So first thing, here we are looking at a box, and honestly, we don't see anything here. So let's first try to reduce the volume of interest to see what's inside. So I will move to, for instance, feature edges here. I just display just the features. So with the first, we will apply filters on the data in order to extract a better information, which is a clip. And we will clip with a box, which is we will reduce the volume to some specific box. We can select interactively the volume of the box we want to clip it. For instance, just something like that. I don't know. Let's choose this. Let's click apply. Oh, sorry, I did move the box. Okay, let's do it again. Select the box. Okay. Reduce the volume we are looking at the moment, and on the top here. Okay, should be better. Let's apply it. Let's keep with exact. Oh, I have a word here, so let's reduce on this one. No, let's move it like here. Okay, should be perfect. Oh, and click exact to get the exact. Okay, so now we have extracted what the meaningful information in our data set. But what about to display something like the stress, for example? The stress, so it's color with a nice color map. Let's hide the box. You can see in the pipeline editor that we have two eyes here. So you are looking at two data in the same time. So the initial data with some feature edges, we can move. For instance, I move to surface, so I can see don't see anything, or just outline to see the volume, and we have the clip result here. So let's hide the first one. So let's look at the data. So we have some color map here. Not only it's maybe hidden by the resolution, but the range is not nice. So let's change the range to something that is more interesting to look at, between 0 and 1000. And here, that's it. And we can look where are the high value above 1000, and where are the low value on the dataset. So it's very easy to see here. But the mapping between the value and the color could be also managed by the color map editor. So it's very easy to change the color map you want. If you prefer some rainbow color map, for instance, which is very popular in mechanical imaging. Okay, I think the VNC stuff just. So there is several ways. Okay, I will just wait it to reload. You can use the color map in order to change the way you can see the data, and especially to okay, connect again. Sorry for this. So yeah, so I moved to the rainbow, for instance, but if you prefer some Veridis or some Matplotlib and so on, you have lots of available. So let's go back to the cool one. So this is a way to just understand the data, narrow the data. Now let's look at the fluid domain, which is the second data we have here. If I display it, again, we have a big box. So nothing to see here. So let's display it with some outline just to check that everything is okay. So first process we do usually with CFD data is to use some slice. So let's create another filter, which is a slice filter. Apply it on the fluid domain. Let's select a plane. We can do some Z normal, for instance. And I can click some apply. So here my slice is computed. Okay, this is just a plane in a box, nothing fancy to see here. Click the automatic applied. If I move the slice, everything is computed. Let's now select some result on it. For instance, some velocity, and now it's color thanks to the velocity. And if I move again the plane, everything is computed. But as we can see, the color map is not. The range is not great here. So let's change the range. The average velocity is 20 in this simulation. So let's have a minus at 10 and the max at 30 to be between. And here we can easily see where are the high velocity and the low velocity around the blade very easily. And of course, if we move the slice interactively, we can see that everything is computed automatically. I will just change the custom things again. Disable the automatic rescaling to keep the value. Okay, so slice is another very popular way to explore CFD data. So I can now hide the slice. And the last one I want to showcase before the end of this quick introduction to ParaView is the stream tracer. Usually, as we have a vector field, for instance, the velocity, classic way is to use streams, so which is the trajectory of particle inside the vector fields. So by default, choose a line, which is great. Let's change it to less lines, and I will move the lines to something more meaningful here, up in front of the blade with the Y thing. Okay, great. Okay, so you can see in few clicks, I am able to play a bit with the slice and to change it. Just forward should be enough. Yeah. And if I move, the end of the line, everything is computed automatically, and you can understand where the flow is moving and so on. The slice by default are some lines, so sometimes it's more interesting to have more thick lines, and we can use a tube filter to make them more interesting here. Once again, my network is failing. I'm sorry. And as we have also some nice hardware on this node, we can also use some advanced rendering, like the physically based rendering, to put some materials on the data and to do some realistic renderings, including some ray tracing algorithm, for instance, which means that we move to an advanced way to represent the data. So about ray tracing, we have two libraries available by default in ParaView. You have the Osprey library, which does ray tracing on CPU. So if you have a cluster when you don't have GPUs, here we have powerful GPUs, but you can use it. And if you have some GPU, you can use also the NVIDIA extension like these RTX, or optics. So here I just applied some tubes. Let's change the size of the tubes to something close, and here it's really nicer to see. And of course, again, I can move the string tracer and to see the tubes updated in real time if I want to. So just to showcase to you the ray tracing things, if I enable here, we can move to, for instance, the path tracer and to have some nice advanced rendering. Okay. So first, it's a bit blurry, and if we set a nice sample per pixel, we have some nice shadows computing on the floor while you are doing your post-processing. I think I will stop here about the ParaView presentation and leave the floor again to Théo to close this webinar. Thank you.
Thank you, François. Thank you for this presentation. I think the post-processing is always one of the most satisfying part of the whole CFD workflow, because it's like the end of a whole case that has run on your infrastructures. So thank you. As you can see, we've showed how you can run a whole case from the pre-processing to the post-processing on resources and resources that are made available to everyone. This is the main objective that we pursue. As a follow-up to this webinar, what we want to do is to allow you to try the case that we've showed here, so the motor blade case. And to do so, you will be sent the actual inputs file that are used for the simulation with a quick guided tutorial on how to launch it on the simulation. And this is the QR code that you can use to create your account on the platform and gain instant access to CodeCertian, ParaView, and everything that we've showed today. I said it at the start of the webinar, but for everyone that has joined since, if you have any question, you can use the side. You can use the 9 dots that are on the bottom right of your screen to ask the question. I can see that there is a question more for you, Maxime, I think. Are any solvers from EDF GPU compatible?
Yeah, it's a very, very good question. So I believe that here we are talking about solvers, so not about ParaView and Salome. So yeah, there is some ongoing process working on CodeCertian for GPU. So we see EDF developing team is seeing some speed up, and there will, in the next future, they will have a version of CodeCertian on GPU. Will it be open source or not? I can't say for the moment, but it's an ongoing process and really interesting. It's not the case for GPU, let's say for structural solver analysis. It's not something that is very relevant for the moment, but for CodeCertian, in the next future, you will have a version based on GPU infrastructure. Yeah.
Thank you. There's another question regarding both Symvia and Qarnot this time. Is Code Aster available or will be available with Qarnot? So yes, there are integration that are taken on so that Code Aster will be soon available on the platform, just as CodeCertian is currently. Does Qarnot platforms have GPU hardware? Sorry, GPU hardware. Yes. So the presentation that you just saw on ParaView was made using our GPU hardware. So those are NVIDIA A6000 GPUs that we can provide. Does Qarnot infrastructure support the study manager option feature for Code Saturn, sorry. So the study manager.
So yeah, the study manager is the way you can launch a batch of simulation, and you can have access to a comparison with, let's say, some probes that you have inside the simulation. So it's something that can be done and is done by EDF on clusters. So for the moment, we don't have developed this with Qarnot, but it's really related to the time that we dedicated to it, but there is no luck to do so. So if you are interested, it's good to know, and we can work on this with Théo. Yeah.
And as you mentioned also, what you can do to have a batch of simulations is that everything I've showed you on the launch of a simulation, you can also use Qarnot's SDK, so Python or directly the API or the command line interface to launch simulation and to have a more a more bulk approach to the campaign that you may have on your cases. I think we've covered all of the questions, at least that are in the chat right now. So there's a new one. Thanks for the presentation. You're welcome. One question for Maxime: how steep is the learning curve? Sorry, for moving from a commercial CAE software package, ANSYS or Abacus, for example, to Codaster?
Yeah, it's very relevant question on this part. So it depends on which application you have of ANSYS. Is it the workbench that you use or not? You have the graphical interface that you can use with Salome and Codaster. It's called Salome Mecha, and you can do all the steps that you have with ANSYS Workbench in the same way. The only thing is to know where are the buttons of it. And if you are more in the scripting part of simulation, let's say that is based on Python, if you want to run simulation with Codaster. So if you know Python, you won't be lost for launching Codaster. So I won't say that it's something that is painless. You will need to take some time to learn this new tool, but it's something that we can help, and we can bring some support for this. And I hope our tutorials at least help for this kind of migration between commercial CAE and open source one.
Thank you. So a new question regarding the interface between Code Saturn and Codaster. How have you done the data transfer from Code Saturn to Codaster? What are the challenges faced? So
yeah. So there is, if you talk only about data, about results that you want to share, input, output, there is a format dedicated to the software, which is called MED format, and it's made for CFD solver, Code Saturn, and the CAE solver, Codaster. So if you want to share the data, you can rely on this format to communicate between the both solver, but there are some development in progress in order to make this more, let's say, easier. But based on the use case that you have seen today, we will have a tutorial in the next week explaining how to do this, how to run Code Saturn and then Codaster. So it will be on our GitHub.
What do I need to change in my code to make my local simulation work for HPC? Do I need to learn Slurm and other HPC tools? So this will be regarding the launch of your simulation. On Qarnot, we have several solvers that are already integrated, and we've done the integration part so that it can be displayed, it can be dispatched, sorry, on Qarnot's infrastructure. So you do not have to learn Slurm to launch simulations on Qarnot. This is one of the things that we take on. We have our own in-house orchestrator, and we organize the workload so that it can be dispatched on our hardwares depending on your case, depending on the hardware needs, and everything that you've required for your launch. This will be managed on our end, and you don't have to learn Slurm to use the HPC platform that we provide. What about specific version availability on Qarnot? For instance, if we still use an old version of Code Saturn. So this is something that we can actually discuss fairly easily. Once we have integrated one software, it is pretty straightforward to upload new version, depending on certain particular cases, of course. But this is something that you can reach out to us to organize if you know in advance the particular version that you want to use, especially for Code Saturn, because we have this partnership. It will be very easy to integrate the new version that you require. Does your orchestrator automatically choose the best number of CPUs? So this really depends on the case that you are about to run. So this is something that you can play with. You have a way on launch to select the number of working cores that you want on each server that will be working on your case. But this is something that we do not automatically choose for you. We have suggestions that are broad suggestions, but usually we suggest that you may try things out to see what is the best ratio for your particular case. During our benchmarks, we've seen cases where using, for example, for the Xeon servers, 24 out of the 28 cores was the optimum, other were 26 was the optimum. This really depends on the case that you are trying to run. Okay, I think that if we've covered all of your questions, this is a good place to wrap things up. So once again, thank you for being with us today. Thank you to Maxime and François for joining us for this webinar. And the replay will also be available if you want to rewatch some parts of or share the actual replay internally. This is something that we will reach out to you with so that you can use it. Thanks again, and see you next time.
Thank you. Bye.
Bye.